Jnanam paramam dheyam. Knowledge is supreme.
This, of course, is a continuation of what we have been discussing in the last few classes, time-dependent perturbation theoretical treatment of semi-classical treatment of interaction of radiation with matter. And to keep things simple, we are working with a two-state system. One is designated L, one is designated M, and now I can write L lower and M higher with confidence, because we have already seen that we have eliminated the other possibility where L is higher. Essentially, L means the level from which the transition begins. M is the destination level where the transition terminates. Okay. So, if L is below M in energy, then we are talking about an absorption. Okay. As we have said, since we are using perturbation theory, what we do is we write the Hamiltonian like this. Hamiltonian of this two-state system is written as the unperturbed Hamiltonian plus a first order perturbation term, and this first order perturbation term, as we have already, is minus mu x into Ex. We are working in x direction only. Mu x is the x component of dipole moment, Ex is the x component of the electric field associated with light. And so, once again, please don't forget, when we formulate the Hamiltonians in the wave mechanical treatment, all our formulations are actually classical in nature. We are considering a classical electrostatic interaction between the dipole and the field, that is all. So, this Ex we had written as 2Ex0 cos 2 pi mu t, alright, and then this had boiled down to minus mu x Ex0 e to the power 2 pi I mu t plus e to the power minus 2 pi I mu t. Is that right? Right? So, this was the formulation of the perturbation. What about the wave function? We said the time and space dependent wave function psi of the two-state system is given as a linear combination of wave functions of the two states. Okay. And it is very important to remember that this coefficient Cl and Cn are time dependent. At initial times, we said Cl tends to 1, Cm tends to 0. Of course, they are not exactly equal to 1, not exactly equal to 0 at any time after 0 time. Okay, 0 time is the time when we switch the perturbation on. And since the question was asked once, the perturbation remains on. It's not as if the perturbation goes off. If perturbation goes off, then you have what is called relaxation. That's a different ball game altogether. Okay. From here, I think so far we have reached here. Cm, I'll just write Cm for now. Actually, it is absolute value of Cm. Cm has turned out to be Ex0 multiplied by psi m mu x psi l integrated over all space. Now, this psi and this psi, what kind of wave functions are these? Yeah? I cannot hear you. What is the difference between this psi and say this psi? So, this capital psi is space dependent as well as time dependent. Actually, it is a product of the space dependent and time dependent part. This is only the space dependent part. It is, I have said it perhaps 5 times already in this course or more, but I am saying it so many times because it is important that we do not have any confusion here. This integral is only in terms of spatial coordinates. It is very important that you understand that. What happened to the temporal coordinate? The temporal coordinate has come out here like this. For absorption process, we have got the temporal, we have got this term to be, denominator is Em minus El minus H nu. What is the numerator? What is the numerator? E to the power, what happened? Oh, you are telling me the answer, is it? No, what is it? 1, right. I was putting that exponential, I keep forgetting that 1. One minus exponential 2 pi I by H into Em minus El minus H nu into T. Is this expression complete or is there anything else? Yeah? Minus we will neglect for now. Okay? Because in fact later on when we do an integration, the limits are between minus infinity to plus infinity. That will get reversed. So that minus sign will come from there. So for now we will just write the absolute value. Is it complete? I am not missing any H, 2 pi, anything, but those are things I always miss while writing an expression. This is complete? Okay. Now what we will do is, we will start from here. This is our starting point for today. And don't forget, we are only talking about an absorption process, this kind of a situation. Okay. So what I want to do now is, I want to find what is Cm star multiplied by Cm. Because as you know, mod square of the coefficient gives you the probability, right? Probability of that wave function in the combined wave function. If you have any doubt about that, in this grey wheel sheets that I am going to share today, it is worked out. You can have a look at that. Okay. Well, I forgot this. So what I will do is I will simplify this a little bit. Let me write A is equal to Em minus El minus H nu. I will simplify a little bit, multiplied by pi by H into T. Why did I write this strange expression all of a sudden? Because a strange expression is there. I am trying to simplify this exponential term. Okay? It is just that I have left the 2 outside and I have left the I outside. Except for that, you have see pi by H multiplied by Em minus El minus H nu divided by T. Yes? Okay? That's all. I am going to write it in terms of A, nothing else. Now, why have I left the 2 outside? I might as well have taken 2 inside. I have written the 2 outside because I have the benefit of hindsight. We are not the first ones in the world to be working this out today. This has been worked out not 100, maybe 80, 90 years ago. So, we already know that if we leave the 2 outside, our next step is going to become a little simpler. Otherwise, we could have just taken it. It does not matter. Okay. So, what we will do is, what is the denominator then? What is the denominator? Em minus El minus H nu, that will be equal to HA divided by pi t, isn't it? HA divided by pi t. So, what I will do is, I will write this expression as HA, I just write A here, I might write pi by H T t somewhere here. Okay? You understand what's going on? I'm just writing this in terms of a, nothing else. What is the numerator? Instead of 1 minus exponential all this, what can I write? 1 minus e to the power a or 2a? 2a. 2ia. So this becomes much smaller. This becomes 1 minus e to the power 2ia divided by a. So far so good? Okay? Clear? Now, what do I want? In fact, I'll need this later on anyway. So let me write something else also. And let me put it here in the recap section. What is d nu? D nu in terms of, I'll need dA later on, very soon I have to integrate over nu. So it makes sense to write this d nu and dA, that expression also. So I can write like this, dA is equal to minus pi t d nu, is that right? Right? Where is h? H and h will cancel, right? H and h cancels, isn't it? This h and this h, they will cancel. Okay. In fact, I have written it in a little, I'll write it here. I want to keep that portion of the board available. A is equal to pi by h En minus El minus h nu t. Okay, now we have a clean expression. Now what I want to write is Cm star into Cm. What is that? Of course, let's do the easy part first. Well, everything is easy here. Pi square t square by h square, then multiplied by square of the transition moment integral divided by a square. Don't forget, we have a complex number here, so we have to multiply it by its complex conjugate. So 1 minus e to the power 2ia multiplied by 1 minus e to the power minus 2ia. That turns out to be pi square t square h square. In fact, what we have written already has a load of information, but let us just complete it and we'll discuss once. Yeah, Nandan? What is that? Oh, t is not square. Why? And where is ex? What are you saying? T or ex0? Ex0 square is what I missed. You're right. This already has some very important information, but let's wait a little bit. Let's just get done with that little bit of math and then we'll talk about it. Pi square t square by h square multiplied by ex0 whole square, square of transition moment integral multiplied by, well, divided by a square 1, then this into this is what? Minus e to the power 2ia multiplied by minus e to the power minus 2ia, that is plus 1, right? Right? Minus into minus is minus and then, sorry, minus into minus is plus, unless you are education minister in some Indian state, and then you have a plus 1 anyway. Okay, then minus e to the power, maybe I'll write it in bracket for our, so that we see it better, e to the power 2ia plus e to the power minus 2ia. Okay, write it a little bit simpler, pi square t square by h square ex0 square of transition moment integral. Why have I written h? Plus 2 into 1 minus, what is this? E to the power 2ia plus e to the power minus 2ia. 2 cos 2a, right? So I'll take that 2 outside and write 1 minus cos 2a divided by a square. Everybody knows what 1 minus cos 2a is. What is it? What I always remember is cos square a minus sin square a. But then cos square a is 1 minus sin square a. Right? So what will it be? 1 minus 2 sin square a, right? Right or wrong? Any doubt about that? So what I will do is instead of minus cos 2a, I will write 1 minus 2 sin square a. Now the numerator has been cleaned up very nicely, right? 1 minus 1, that is 0. Okay? So you are left with pi square t square by h square ex 0 whole square of your transition moment integral multiplied by, maybe I'll write 4 here. Is that right? Is that right? Is the expression correct? Is it okay? 4 pi square t square divided by h square into x0 square multiplied by transition moment integral. Yeah, sin square a by sin square a divided by a square. Yeah, this is right. Now, what is this? This is probability of transition. Okay? Yes?
It's probability density function.
Why do you say it's probability density function?
Psi and psi is when we integrated it.
Hold on, I'm coming to the integration. Now let us discuss this expression in a little more detail. What do we see here? First of all, we see that probability of transition is proportional to square of transition moment integral. We have been saying all along that if transition moment integral is equal to 0, then the probability is, then the transition is not allowed. Now, we have a little more quantitative way of saying the same thing. We can say that probability of transition is actually equal to square of transition moment integral. Alright. Now, if I go back to those classes on experiments that we had initially, we are talking about absorption, right? For absorption, what is the experimental parameter of probability of transition? Experiment. What we are doing now is theory. Remember, spectroscopy after all is an experimental science. And if you remember the initial discussion we had in this course, we talked about this time domain measurement, frequency domain measurement, and we had talked about an empirical law that everybody knows, Lambert-Beer's law or Beer-Lambert's law, right? So from Beer-Lambert's law, what can you say is the measure of probability of transition? Epsilon, right? Epsilon, right? Absorbance is equal to epsilon CL. Now see, what is C? C is concentration, right? That's an extrinsic parameter. Brute force, increase the concentration, absorbance increases. Length is an extrinsic quantity, right? Increasing the length, that means your light encounters more molecules in its path, that's all. But if you talk about one molecule and if you think of probability of transition, epsilon is the parameter. So now what we learn is that epsilon that we talked about initially must have some relationship with square of transition moment integral. And that is what we are going to learn in the next class, not today. Okay, we'll actually write down an expression which relates absorbance, epsilon, absorption coefficient, and transition moment integral square. But let that be the story for another day. What we learned for now is that probability of transition is directly proportional to square of transition moment integral. Where does the square of transition moment integral come from? Which part of the wave function? Spatial or temporal? Spatial. What is it that we get from the temporal part of the wave function? This is a constant. This is a spatial part. Where is the temporal part? This t square multiplied by sine square a by a square, right? Remember, the sine square a by a square came from all these exponential terms. Where did the exponential terms come from? From the phase, right? From this e to the power I something t, that kind of a part of the wave function. So, the time dependent part of the wave function. So, the spatial part gives us this probability, fine. What the transition, what the time dependent part tells us is that it is the sine square a divided by a square. Okay. If I plot sine square a by a square, what do I get? Yeah, so sin x into sin x. I am not sure how to write sine square. We get this kind of a function. In fact, if you plug in the numbers, you will see that this width is not too much, but there is a finite width nevertheless. So, from the time dependent part of the wave function, we learn that even for, don't forget what kind of a system it is. This is a system, two states, right? L and M. We don't have many states, we only have two states. We have not accounted for any sublevels or any such thing. Even when you have a pure two-state system, what we get from the time dependent part is that you can never get a delta function. You know what delta function is, right? A function that has some value at one particular value of the independent variable, and it is 0 for all other values. So, you will never have a delta function. You will never have a line with 0 width. That is the line shape that you always get, even if you neglect all other line broadening mechanisms. Okay? This line width that you get from here is called the natural line width. Okay? Natural line width. No matter what you do, you cannot change the wave function. So, it is the wave function that tells you that you are going to have at least this kind of a line shape, at least this amount of line width in the spectrum. Okay? This is something that is, in my opinion, a very, very important observation. Yes. T square is also there, of course, but then when I plot this, I have only written sine square a, but you can multiply that by t square, right? It does not matter. So, if you just increase t square, okay, well, there is another aspect of this story. If you increase t square, what will happen? It will just be more, right? Cm star Cm will be more. The whole function gets multiplied by what amount of time it is. So, there is a third important thing that we learn from here. If you keep the perturbation longer, you get a greater mixing of states. You get a greater amount of transition, right? But before going there, do you understand this? Where does this come from? The time dependent part, right? Now, it is actually a direct consequence of uncertainty principle, right? Uncertainty principle, you know, delta E into delta T, right? That has to have some value. Now, what happens is this: if this is your system where you have two states, the ground state has a lifetime of infinity. If you don't disturb the system, it will be in the ground state forever. But excited state does not have an infinite lifetime, it has a finite lifetime. If you promote the molecule to excited state, what will happen is that it has to come back sooner or later, right? The average time it spends in the excited state is called the lifetime. Okay? So, now see, what is the uncertainty in time associated with the ground state? It can actually be infinity because it is always there if you do not disturb it. What is the maximum allowed uncertainty associated with the excited state? That cannot be more than the lifetime, isn't it? If I say my height is 5 feet plus minus 30 feet, does that make any sense? If I say my height is 5 feet plus minus 5 feet, that also does not make sense unless I am a quantum mechanical object. We are dealing with quantum mechanical objects here. So, maximum allowed uncertainty is of the same order as what the value is. Okay. So, always there is an uncertainty in time and that brings in an uncertainty in energy as well. So what I have drawn as one line is really an ensemble of states with a small maybe but finite distribution of energy. So the correct picture here really is something like this. There is an uncertainty in energy of the excited state. That is what brings in natural Linewidth. Are we clear so far? Because what we have discussed so far is actually profound. Are we clear? Any question? Can I go ahead? Let's do that. Now, if this is the case, then when I want to talk about the probability of transition, I am faced with a dilemma. What do I define as the probability of transition? I can say it is the probability here, but then in that case I will be neglecting this and this and this and that. Even if you come here, there is a small but finite probability, isn't it? So the correct way of handling this is to talk about a probability that, as somebody was saying, that is integrated over the band. Okay? If I integrate, then the probability that I get is the probability of that transition. Once again, let us be very, very careful here. The reason why I want to be careful is that you have done experiments in electronic spectroscopy and you are associated with broad bands, right? When you do an UV measurement, don't you get a broadband? We are not talking about that kind of a broadband. That broadband arises because there are actually many states. It's not a two-state system at all. That's a different issue altogether. We are talking about a situation where there is no other line broadening mechanism. We have two states. Whatever uncertainty in energy is there, that is the only contributant to the line width. In that case, what we talk about then is we should talk about a probability that is integrated over the band. For the records, let me say once again that this line width is not too much. It is small, but it is not zero. Okay. Yes.
What are those small bits? The large bit is the band, right?
Yes.
What are the small ones?
So it signifies the periodicity of a comparatively higher probability of transition to some state. So as I said, there is a distribution of states, right? But then the thing is, the distribution comes out of a periodic function. So that's why the probability is also periodic. So there are some transitions which have a little higher probability. For example, this transition has a little higher probability than this one, and definitely a higher probability than this one, but it dies off quickly. So this arises out of the periodic nature of the wave function itself. Okay? Can I go ahead? Great. Now I am going to need this. What we want to talk about then, let me define this probability of transition. I will write it as P L to M as integral Cm star Cm d nu. That is the probability integrated over the band. Don't forget, the band is for a single L to M transition. Okay? Right. What will it be? That will be equal to, I will just write the constants outside, and integration is over nu. So I can take P as constant. That's not a problem. But what I have to do is, I have to, since this thing is written in terms of A, instead of d nu, I will write this. Okay? This d nu becomes minus pi t into dA. Yeah. Minus dA by pi t. And what I will do is, I will neglect this minus also. We have not written one minus earlier, isn't it? Remember, we got a minus, and this is the reason of the deviation we had from the textbook. They have not written any of the minus signs. Since we have followed their convention and omitted the minus sign earlier, I will omit this one as well. So this I will write as dA by pi t, then this becomes, this is what it is, 4 pi square by pi, right? So this is a pi, t square by t, so this is a t divided by h square into ex0 whole square, square of transition moment integral have I written everything? Integral sin square a divided by a square dA. What are the limits of the integral? Well, minus infinity to plus infinity. Okay, minus infinity to plus infinity, considering there is no other transition. Okay, that doesn't matter anymore. Is it okay? Done? Sure. Now, what is the next step? Next step is work out the integral, right? What we will do is we will use a standard integral. This minus infinity to plus infinity integral. We will look up a table and the table will tell us that this value is actually pi. Okay, minus infinity to infinity is a standard integral, right? Sin square by a square, that turns out to be pi. So then what does it become? That is a pi. So this becomes 4 pi square t divided by h square multiplied by ex0 square. Maybe I will write this t here at the end, multiplied by square of the transition moment integral. Yes. Yeah. Yes. That's right. But now we will deviate from that. We have considered it at a time t, at particular time t after perturbation. So we don't have to integrate over it. Now the thing is this is the penultimate step of where we are trying to get. The ultimate step is, you are talking about intensity. Remember when we talked about the experimental part of spectroscopy, we were talking about intensity of absorption, intensity of emission. What is the definition of intensity? Then? No, it's not high probability or anything. I said intensity. I did not say high intensity or low intensity. Hey, last bench, what is the definition of intensity? Right. Answer has come from third bench. Anyway, but at least we have your attention. You are right. Per unit time, okay? It's basically rate. It's a rate, right? So what we'll do is we'll convert this to per unit time as well, and we write it as dP L to M dt is equal to 4 pi square divided by h square ex0 whole square in transition moment integral square. That's it. This is your expression for rate of transition. Okay? Will you agree with me that this rate of transition is the one that is directly correlated with intensity of absorption, intensity of light absorbed, right? Rate of transition, right? So that per second is already there. Okay. Now let us write it in terms of something else. We are going to make two substitutions in this expression. First is, so far we have been working with mu x. Okay. Now it is time that we write it in terms of mu. So for an isotropic radiation, what happens is that you can just write mu x as mu divided by 3. Okay. So I can write that as mu by 3. That will take us a little closer to the expression that we are trying to get, and this is the general expression for transition moment integral, don't forget. And we will do another thing. Generally, when you talk about light, of course, this is something that you have, unless you have taken a course in optics, this is one part where you will have to just believe me what I am going to say right now. What you generally want to work with when you talk about light is not Ex0, but this. rho of nu. Have you encountered rho of nu somewhere? Yeah? Never? Rho of nu is energy density. Yes, black body radiation. So, in black body radiation we have encountered it, right? So, when we talked about Planck's law and all that, rho nu. Rho of nu is something that is more familiar, and now you just have to believe me that in the system that we are using here, it is equal to Ex0 square divided by 2 pi. Okay. Of course, in the exam, I have to give it to you. I cannot just expect you to remember this. Okay. Let us substitute that also. I'll write rho of nu here, and I'll divide it by 2 pi. So, this becomes a 2, this becomes a pi. 2 pi divided by 3h square, is this right? I'm going wrong somewhere. Where did I go wrong? Huh? So what should I write in place of Ex0 square? I should write 2 pi, right? So actually 2 pi goes here. 8 pi cube, right? 8 pi cube divided by 3h square. I made a silly mistake, that's all. Okay. Rho of nu equal to Ex0 square by 2 pi. So you are substituting for Ex0 square. Ex0 square has to be substituted by 2 pi into rho nu, and that's what you get. So this is a rather important equation, a rather important rule, you can say. It is called Fermi's golden rule. And as I think I have told you earlier, Fermi's golden rule was not derived by Fermi. Fermi just saw it and said, oh man, it's such a great rule, it's a golden rule. And then it took the name Fermi's golden rule. Now, why is it that Fermi was so impressed when he saw this? Does this look impressive? It doesn't, right? It's like any other expression. So, why is it a golden rule? It's a golden rule because first of all, it brings in an idea of dynamics, right? It's a rate on the left hand side. Secondly, if you look at the right hand side, you have a constant multiplied by an intrinsic quantity, right? Probability, right? Intrinsic quantity here multiplied by an extrinsic quantity, energy density of light. And that kind of opens up the field where we can discuss a lot of things now. Okay, that's why it's called the golden rule. And it's important to remember that this Fermi's golden rule essentially is an expression of the rate of transition as a product of two factors. One which is extrinsic to the system, the transition moment integral square, and the other that is actually a property of the, I was a little wrong there, a property of light, rho nu. So now you can model this transition like a chemical system where two molecules are reacting, right? You can think that this is one kind of concentration which is related to concentration of, which is related to the system. This is another kind of concentration, energy density, right? So kind of concentration of photons you can think. So now that opens up the possibility of expressing this radiation matter interaction as a sort of bimolecular reaction between molecule and light, matter and light. And whenever we have that, then we chemists are in familiar territory, because this is then, if you look at it carefully, it's like a rate equation, right? Rate of reaction, rate equation of, you can say, second order. Okay, it's something like you are familiar with this kind of an a reaction, say A plus B forms products. It is not necessary that the rate will also always be a concentration of A multiplied by concentration of B, but suppose it is, then what is it? Then you can write dP dt is equal to some constant K multiplied by concentration of A multiplied by concentration of B, right? Which is exactly similar in form to your Fermi's golden rule. So, Fermi's golden rule now lets us move towards a territory where you can do some very easy kinetic treatment and get some idea about the transition. And that is what Einstein did. What Einstein did is that he set up this kinetic treatment of the two-body problem. He considered two levels like what we have done. He considered that there are three possibilities actually. One is induced absorption. One is induced emission. I hope you have not forgotten that when we talk about emission so far, it is always induced emission because light is involved. Third thing that is not something we have considered so far is spontaneous emission. Actually, we are more comfortable with the idea of spontaneous emission, right? Because we know about nuclear decays and all. You leave something in excited state, it just decays by itself. Doesn't need any help from anything. But then in the treatment that we have done so far, spontaneous emission has not come at all. So what Einstein did was that he kind of used this as one of the terms and he set up a rate equation involving two states. First term was for absorption, population of the excited state by absorption. Second term was for depopulation of the excited state by stimulated emission. Third term was for depopulation of excited state by spontaneous emission. So the first two terms are, you can say, of second order, third term is first order. And hence, he took us to an interesting discussion of when do you have stimulated emission, when do you have spontaneous emission as the major radiative deactivation pathway. And that eventually takes us to a very useful discussion of lasers and laser spectroscopy. So tomorrow, we are going to at least begin with Einstein's kinetic treatment and then let's see where we go.